Okay, good morning, Alpha. So today we're going to discuss about the flow path immerse object, the first part. So before we going further to the theory and also the calculation, we will watch a video first.
Water softeners contain two separate chambers, a brine tank and a resin tank. And the resin tank is where the water softening is actually taking place. Water softeners make use of a process called ion exchange to remove the hardness ions from the water. These hardness ions are primarily calcium and magnesium, but they can also include things like manganese, iron, and radium. The resin tank contains a bed of small beads that have sodium ions electrostatically attached to them. The water softener pumps hard water through this bed of resin beads, and the hardness ions are exchanged with the sodium ions. Now, eventually that resin will fill up with hardness ions and it can't soften any more water. At that point, the water softener must regenerate. The water softener goes offline, and this is where the brine tank comes in. Salt brine from the brine tank is pumped into the resin, and that salt brine washes away the hardness ions and replaces them with a fresh layer of sodium ions, so the softener can then go back online and resume softening more water. So I hope this has helped you better understand how water softeners work. If you've got more questions, please let us know.
Okay, so I hope you do understand what the video trying to say. If you do not understand yet, you can just go back and rewatch the video. Now, I have the question now. Yeah, in the resin tank, yeah, based from the video, in the resin tank, yeah, which one is the immersed object, and then which one is the fluid passing over the object? Yeah, so the answer is the immersed object, yeah, is the resin beads. Yeah, because it is the solid that is immersed in a fluid. Yeah, while the hard water is the fluid passing over the immersed object. Yeah, so in this subchapter, we will talk about the fluid flow past the immersed object. So of course, there will be two types of items here. First is the immersed objects, yeah, which is usually in a solid form. And then the second is the fluid passing over the object. So it's a fluid, yeah. So the immersed object in that previous video is the resin beads, while the hard water, yeah, is the fluid passed over the immersed object. Okay, so in this subchapter, we will discuss about the behavior of the fluid when it passes the immersed object. Yeah, there are several outlines here, yeah, that we want to discuss today, and then it will be also continued in the part 2 of fluid pass immersed object, yeah, in the next class. Okay, so many chemical engineering process, yeah, uses this, type of fluid pass immersed object, yeah, such as filtration. Yeah, so in the filtration, there will be two phases, yeah, solid and liquid, yeah, where in the filtration, we want to separate solid from the liquid, yeah. So of course, since it has two types of phases, yeah, when it is flown, yeah, into the filtration system, yeah, the fluid flow, yeah, will pass over the immersed object, will pass over the solid. Yeah, you can imagine, yeah, when we want to, let me draw it. Yeah. So let's say we have a filtration here. This is the filter, yeah, and then slurry will have solid, yeah, and it will also have liquid, yeah. Now, when it goes into the surface of the filter, yeah, the solid will retain here, yeah. Now, while the liquid will pass through, yeah, and goes out here. Yeah. So as you can see here in the layer of the solid, yeah, the liquid will start to pass through the layer of solid. Yeah. So in this part, there is a fluid flow pass over the solid, the immersed solid. Yeah. And it goes as well with the ion exchange. Yeah, as you can see from the previous videos. Yeah. The resin bits is immersed inside the hot water. So the hot water will pass through the immersed solid. Yeah. Yeah, so I hope you do understand. Yeah, if we have a filter here, and this is filter. Yeah. And then we have a solid and liquid. Yeah, so this is solid and this is liquid. Yeah. When it goes into the filter, of course, there will be a layer of solids. Yeah, that is retained in the on the surface of the filter. Yeah. So when the liquid wants to pass through the solid layer and also the filter and then go out, yeah, as a filtrate, yeah. So this phenomenon, yeah, we call it as a fluid flow past the immersed solid or immersed object. Okay. Nah. Nah, the flow profile for the fluid past immersed object, yeah, can be seen on the GIF on the right. Yeah, so as you can see here, the fluid coming from the right to the left. Yeah, while it first meet, yeah, while the fluid flow first meet the immersed object, yeah, it will have a stagnation point, yeah, at this exact point. Yeah. Okay, so in the back side or in the rear side of the particle, yeah, so in this point, yeah, in this exact point, yeah, the fluid flow, yeah, will not have any velocities. Yeah. So in this rear side of the particles, yeah, when the fluid first meet the particles, yeah, first meet the immersed bodies, yeah, at this point, yeah, the velocity of the fluid is 0. So that's why we call it as a stagnation point. Yeah. However, the fluid do not stop here, right? Yeah. So it will go into the side, follow the shape of the surface of the immersed bodies. Yeah. Nah, and then it will start to form a boundary layer. Yeah, where the liquid film on the solid surface is formed. Yeah, so in this side, so this is the stagnation point. Yeah. So when the fluid first meet the particles, yeah, it will have a stagnation point at this exact point. Yeah. So at the back or at the rear side of the particles. Yeah. And then it will goes up and also goes down. Yeah. Following the shape of the immersed bodies. Okay. And then it will have a boundary layer. Yeah. Or a liquid film on the solid surface. Yeah. Now, after it passed half of the sphere, you can see that in this point, yeah, the flow separates, yeah, into several directions. Yeah, there is directions come here, there is direction comes there. Yeah, so we call this as a separation point. Yeah, now and then at the opposite side of the stagnation point, yeah, we have the formation of wake and eddies. Okay. Yeah. There are two types of drag that is formed in this type of flow. First is the frictional drag. Second is the form drag. Yeah, so for the frictional drag, Yeah, it is exerted by the fluid on the solid surface due to skin friction between fluid and solid. Yeah, so as you can see here, yeah, the fluid flowing from the left to the right. Yeah, however, when it meets the solid surface, yeah, there will be a friction, yeah, between the solid and the liquid. Yeah, so this friction, yeah, is called as a frictional drag. If we have a smooth surface, yeah, of the solid, of the immersed solid, so of course there will be only a small frictional drag. However, if we have a rough surface, yeah, there will be a large frictional drag. Yeah, because there will be a lot of eddies inside. Yeah. Nah, for the form drag, yeah, it is caused by the direction change of the fluid from horizontal flow to a gradual slope flow. Yeah, so as you can see here, first is the horizontal flow. Yeah, however, after it meets the surface of the immersed bodies, yeah, it will change direction, yeah, following the shape of the solid. Yeah. Okay. Nah, and then yeah, when the fluid flow got into impact with the front part, yeah. So let's say this is the fluid and then it goes like this and then it got into the impact with the front part of the solid surface, yeah, it will have the fluid flow, yeah, coming up, yeah, coming up following the shape of the solid, yeah, and then it will also accelerate. So the velocity will accelerate due to the impact, yeah. So when the fluid flow comes into impact with the front part of the solid surface, besides it will change in the direction to go upward, it will also accelerate, yeah, because of the impact. Yeah, however, when it goes down, yeah, so after it passes through the peak of the solid surface and it goes down here, yeah, it will decelerate, yeah, as the velocity will become slower. Yeah. Okay, now if we have a streamlined bodies, yeah, yeah, there will be a small form drag, yeah, because it has a streamlined bodies. However, if it has a blunt bodies, ya, jadi tumpul, it will form a large form drag. Okay. Nah, so depending on the solid shape, yeah, the fluid behavior and the magnitude of the skin and form drag, yeah, can be seen on the figure on the right. Yeah, the more streamlined, yeah, so this is a very streamlined solid shape, yeah, and then this is a little bit, you know, streamlined, and this is still streamlined, but it's you know, have a, you know, higher height, ya, lebih tinggi, ya, kamu lihat ini lebih tinggi daripada ini lebih tinggi daripada ini. Nah, and then this is the not streamlined shape, yeah, because it has a very you know, very tall height, but very, you know, thin, yeah, very thin, yeah. So this is a blunt shape, yeah. So as you can see here, the more streamlined the solid shape is, yeah, there will be less form drag and wake or eddies that is formed, yeah. So if you can see here, yeah, more streamlined, higher screen friction, yeah, less form drag. The more it's not streamlined, higher foam drag, lower skin friction. Yeah. Okay. And as you can see here, when it has higher foam drag, yeah, it will have ADs. Yeah, higher foam drag, higher formation of ADs or wake. Yeah. But the more it is streamlined, there will be no wake or ADs. Yeah, the more streamlined, only skin friction, yeah, governing the fluid flow. Yeah, however, for the blunt objects, yeah, it will have a very high foam drag, but no skin friction. Okay. Nah. Okay, so I hope that when you listen to this YouTube videos, you also open the Jan Copley's book, so that you can just directly note it. Yeah. The every single equations that you will use in the calculation. Yeah. Okay, so for you to calculate the drag force, yeah, either it's the foam drag or skin frictional drag, yeah. Now to calculate the drag force that is formed in this type of flow, yeah, we have to find the drag coefficient, or we call it as CD, yeah, using equation 3.11. Okay, so equation 3.11 is for you to find the drag coefficient. Okay, so please take a note, yeah, on your Jan Copley's book, that 3.11 is for you to find the drag coefficients which will be used to find the drag force. Okay, so please open the Jan Copley's book and then make a note on every single equations that you have to use in the calculation. Okay, nah, and then in equations 3.12, yeah, you can find the total drag force, or FD. Yeah. Okay, so FD, or total drag force, can be found using equations 3.12. Okay. Okay, so CD, drag coefficients, is 3.11, while FD, or total drag force, can be found using 3.12. Nah, and then, yeah, we have also Reynolds number for the solid immersed in the flowing fluid. Yeah, so this is the Reynolds number for the solid immersed in a flowing fluid. Yeah, so it's not the Reynolds number of the flowing fluid, but this is the Reynolds number for the solid immersed in a flowing fluid. Yeah, can be calculated using 3.13. Yeah. Okay. Okay, let me try to open. Yeah, so this is CD. Yeah. So 3.11 is for you to find the drag coefficient. Yeah. While this FD, yeah, after you find CD, yeah, you may try to find this FD. Yeah. 3.12. Yeah. And then 3.13 is the Reynolds number for the solid immersed in a flowing fluid. Okay. Okay. So let me go back to the PowerPoint. So yeah, after equations 311, 312, and 313, yeah. Nah. Oh, wait a minute. Nah. Okay, so please read your Jönköp list, yeah, on page 122 to 123 in subchapter of 3.1a.2 carefully, yeah. Please read it carefully. And then please try to answer the questions below, yeah. So, yeah, the question is, why the particle area used in the equations 311 and 312, yeah, is AP equals to pi times particle diameter square over 4 for sphere and L times particle diameter for cylinder. Yeah. Yeah, why not pi times diameter of particle square for sphere and pi dpl plus pi dp square per 2 for cylinder? Yeah. Why? Yeah, so if you see here, oops. Yeah, so you see for cylinder, yeah, they said it's L times dp. Oh, sorry. While for sphere, it's pi times dp squared per 4. Yeah. Well, actually, the surface area for cylinder, yeah, it's dp times pi times L plus 2 times, yeah, 2 times pi times dp squared per 4. Yeah. It should be like that, right? Now, why? Let's say for cylinder, yeah. Okay. Yeah, it should be pi times d times L, yeah, for this area, yeah, for this, yeah. And then for these two circles, yeah, it should be 2 times pi times dp squared per 4, right? But why they use this L per dp, L times dp? Yeah. Nah, the answer is in the next slide. Wait a minute. Nah, because the area used in the equations is the projected area of the 3D objects. Yeah, so the area used in the equations is the projected area of the 3D objects. So as you can see, yeah, as you can see, yeah, for sphere, the projected area is a circle. So that's why it's pi times diameter of particle square per 4. Yeah, it's a circle. Yeah, so it's pi times diameter of particle square per 4. While for cylinder, the projected area is a rectangle. Yeah, so that's why it's L times dp. Yeah. Okay. So what we use in the equation is the projected area, not the actual area. Yeah. If it's the actual area, yeah, if it's the actual area, then of course it's the area of the, of this side plus this side and the back side. Yeah. However, since it's projected area, you can see it's a rectangle. Yeah, so it's L times dp only. Yeah, while for the cylinder, while for the sphere, The projected area is the circle. So of course, we can just use the equations for circle, yeah, to calculate the projected area of a sphere. Okay, so now we move to the next section. It's the flow past spheres, long cylinder, and disk. Yeah. So, yeah. Flow past sphere, long cylinder, and disk. Yeah, so long cylinder and disk are equally, so this is actually a cylinder. Yeah, so this actually are a cylinder, but it has a very short length. Yeah, a very short length. Okay. Nah. And then in this section, yeah, we will assume, yeah, until this chapter ends, yeah, we will assume that the long cylinder and disk, yeah, it will be immersed perpendicular to the fluid flow direction. Yeah. Yeah, so it will be assumed until this chapter ends that the long cylinder and disk are immersed in the perpendicular to the fluid flow direction. Okay. So if the fluid flow direction is horizontal, so the long cylinder and disk, yeah, will be placed vertically. Okay. Nah, so as previously mentioned, that the drag coefficient or CD, it is pretty much affected by the Reynolds number. Yeah, so actually you can see from the figure 3.12. Now let me open 3.12. Here, yeah. So you can see that the drag coefficient is pretty much affected by the Reynolds number. Yeah. So as you can see here, this is for cylinder, the long dash line. And then disk is the short dash line, while the sphere is the lines, yeah, the normal lines, okay? Okay. So you can try to find the drag coefficient by using the Reynolds number, yeah? Nah. So you can use directly figure 3.12, or you can use these guidelines to determine the drag coefficients or CD. Yeah, so if the Reynolds number, yeah. Sorry, let me try to check. So if the Reynolds number of the immersed solid is between 0 and 1, then you can use equations 3.14 and 3.15, yeah, to find the CD. Okay. Now, however, if the Reynolds number is in between 1 and 1000, then you can use figure 3.12. Yeah. Now, while if the Reynolds number, yeah, is between 1000 to 200,000, then the CD for spheres, yeah, the drag coefficients only for spheres is 0.44. While if it's in another shapes, then you can use figure 3.12. Yeah. Now, if the Reynolds number is in between 200,000 up until 500,000, then you can use figure 312 for all shapes. Yeah. While if the Reynolds number is higher than 500,000, the drag coefficient for sphere is 0.13, for a cylinder is 0.33, while for this is 1.12. Or you can just use figure 3.12 for all Reynolds number. Yeah. Okay. So please read the example 3.11 and 3.12. Yeah. Okay, so we will discuss about example 3.1 and 3.2. 3.11 and 3.12. Yeah, so for 3.11 first, so we have air at this temperature and also pressure. Okay. Flow past a sphere having a diameter of 42 millimeter at a velocity of 23 meter per second. Then we are asked to calculate the drag coefficient and also the force on the sphere. Okay, so we have the diameter of the particles, yeah, dp 0.042, and then this is the V0, 23, and then the density of air at the specific temperature and force and pressure is this, and also the mu is this. Yeah, we got this density and viscosity from appendix A3. Yeah, and then using the equations to find NRE or Reynolds number, yeah, we can find that the Reynolds number is 5.8 times 10 to the power of 4. And then we can try to find from figure 3.12 for the value of CD, and we found that the CD for this sphere is 0.47. Yeah, so we know the drag coefficient is 0.47. And then we can substitute the CD, yeah, to this, yeah, to equations 312. Yeah, CD times V0 square per 2 times rho times AP. Now AP is the projected area of the sphere, which is in a circle shape. Yeah, so it's pi times dp squared per 4. Yeah. So you can put all the value here and you can find it. The force is, the drag force is 0.1958 Newton. Yeah. Okay, so for example, 3.12, yeah, we have not air, but now it's water at 24 degrees Celsius, flowing past a long cylinder at a velocity of 1 meter per second in a large tunnel. Yeah, the axis of the cylinder is perpendicular to the direction of the flow. Yeah, the diameter of the cylinder is 0.09. Yeah, what is the force per meter length of cylinder? Yeah, so we will try to find the Reynolds number. So we know the dp already 0.09, the V0 also 1, and then density and mu we will find it from the appendix A2 for water. Yeah, so we found that the Reynolds number is 9.817 times 10 to the power of 4. Now, based from the figure 3.12, yeah, for a long cylinder, we found that the CD is 0.4. Yeah, and then we can put the CD here. Yeah, we can put the CD here. Yeah, and then the V0, which is 1 here. And then density from appendix A2 here. And the AP. Yeah, since it's cylinder, it's L times dP. Yeah. And the length, yeah, of the cylinder is per meter. So 1 meter. Yeah, 1 meter times the dP, 0.09. Yeah, so we put it here all, and I found that the FD is 62.82 Newton. So any question? If you have any questions, you can write it in the comment section below. Okay. Okay, so we'll move now to the third subchapter, which is the flow in packed beds. Yeah. So the packed bed. Yeah. So this is, I think, a new term for you. Yeah, a packed bed is a system. Yeah, where a fixed bed, yeah, or a packed bed, yeah, of packing materials, yeah, which can be a solid catalyst or an adsorbent or others, yeah, is installed inside a vessel, yeah, in order to spread the fluid flow and intensify the contact between components. Yeah, so if you can see here, yeah, this is the packing materials. The white one here, the small spheres in white, is the packing materials. Now, the packing materials, yeah, the packing materials, yeah, is uh, is filled here, yeah, until this height, and this total small spheres inside, yeah, is called as a packed bed. Okay. Yeah, so the white spheres here is the packing materials, and when you put a lot of packing materials until this height, yeah, so this total packing materials, we call it as a packed bed. Now, this is installed inside a vessel, yeah, with the purpose to spread the fluid flow, yeah, to intensify the contacts between the components. Okay. So I hope that you understand, yeah. So the white one is the packing materials. Yeah, so if you put a lot of packing materials inside a vessel, yeah, up until this height, yeah. So this total bed, yeah, is called as a fixed bed or packed bed. Okay. Now, the shape of the packing materials, yeah, is we have a various shape of packing materials such as spheres, cylinders, yeah, or sometimes irregular particles, yeah, or various kinds of commercial packings, yeah, such as in this part, yeah. So this is the one that is commercially available in the market, yeah, Paul ring, spiral pack, resic ring, bro saddle, yeah, and then interlock saddle, yeah. This is several commercially packing that is available in the market, yeah. Nah, in this subchapter, yeah, we will assume that the packing is uniform. Yeah, so we do not mix the packing in this subchapter. Yeah, in this subchapter, we assume that the packing is uniform. So if one is Lessig ring, so the other also Lessig ring. If one is pearl saddle, then another packing is also pearl saddle. Yeah. Okay. Nah, in packed bed, yeah, we also have a common Reynolds number. So we call it NREP. Yeah. So if the Reynolds number for a fluid flow is NRE, yeah, and then for the particles immersed is also NRE, different different equation. Yeah. For packed bed, yeah, we call it as NREP. Yeah. With the range of 0 to 10 is laminar, 10 to 1000 is transitional and higher than 1000 is turbulent. Yeah. Okay. Nah, for packed bed, yeah, the NREP, I think you can see it from this. Let me see. Uh, Oh, okay. So maybe later, yeah, because for NRE, okay, so for the equations for NRE for packed bed, yeah, it's a little bit different with the NRE for fluid flow, for the common fluid flow, or the NRE for the immersed bodies. So it's a little bit different, and I will explain it later in the next slides. Yeah, but I want to mention about the range here. So it's a little bit different as the common Reynolds number. Yeah, for the common Reynolds number, yeah, turbulent is higher than 4000, right? While laminar is lower than 2100, right? Yeah, but for packed bed, the range is not the same as the previous common Reynolds number, but it's 0 to 10 for laminar, 10 to 1000 for transitional, and higher than 1000 for turbulent. Okay. Okay, so the range is like this for the packed bed Reynolds number. For the equations, I will explain it later because it will be in the next slides. Okay. Nah, for the calculation in packed bed, yeah, we have to know several terms. Yeah, that is maybe also new for you. Yeah, which will be used a lot. Yeah, in the calculation of packed bed. So first is the void fraction. Yeah, so the void fraction is the volume fraction of the interspacing, yeah, between packing. Okay, so it's the empty spaces in bed only. So let's say the bed is from this part up until this part. Yeah, the dash line. You see the dash line in the bottom and the dash line in the upper part. Nah, so from this part until this part, yeah, if the void fraction, yeah, is the volume fraction, yeah, or the empty space, yeah, the empty space in the packed bed. Ya, jadi ruang kosong dari packed bed ini. Ya kan, karena packed bed ini kan nggak mungkin keisi full penuh kan. Ya kalau namanya solid kan kamu taruh bunder gitu, nggak mungkin semuanya keisi. Ya kan, karena kan solid tuh. Jadi pasti masih ada bagian yang kosong. Nah, bagian yang kosong ini or the empty space in the bed, so from this dash line to this dash line, yeah, the empty space, yeah, is called as a void fraction. Yeah, so the interspacing between the packings, yeah, is called as a void fraction. Now, while for the solid fraction is actually 1 minus epsilon. Yeah, 1 minus epsilon. Yeah, so it is the volume fraction of the solid packing. Yeah, so the solid fraction is the volume of the solid packing. Yeah, so the void fraction is the volume of the empty spaces between the solid packing. Solid fraction is the volume fraction of the solid packing. Okay. Nah, specific surface of the particles, specific surface of the packings, yeah, is the surface area of the packing divided by the volume of the packing. Yeah, you can use equation 3.17 for all geometry or shapes. Yeah. Now, for spherical, yeah, the diameter of particle is the diameter of spheres. Yeah. However, while for the other regular shapes, yeah, the effective or equivalent diameter, yeah, because it doesn't have any diameter usually, yeah, it can be found using equations 3.19. Yeah, so let me show it to you. Okay. 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 So you can use this equation, yeah, to find the specific surface of the packing. Yeah. So it's the specific surface area of the packing, the surface area of the packing divided by the volume of the packing. Yeah. So for a spherical particle, yeah, AV can be calculated by 6 divided by dp. Yeah. Okay. Now, for the pack bed, yeah, for a pack bed of non-spherical particle, the effective particle diameter can be defined as dp equals to 6 per AV. Yeah. Okay. Nah, and then we also have one more term, which is called as a ratio of total surface area in the bed to total volume of bed, or we use a symbol of A. Yeah, we can see equations 3.110 for all regular shapes. Yeah, so it's the ratio of total surface area in the bed per total volume of bed. Yeah, or A. Yeah. We can use equations 3.110, yeah, for all regular shape. So this part. This one, yeah. Okay. So A equals to AV times 1 minus epsilon, or 6 over dp times 1 minus epsilon. Yeah. So we go to example 3.13. So we have a packed bed which is composed of cylinders having diameter of 0.02 meter and a length h equal to d. So the length is also 0.02 meter. Yeah. And then the bulk density of the overall packed bed is 962. And the density of solid cylinder is 1,600 kilogram per cubic meter. And then we are asked to calculate the void fraction or epsilon. Yeah. The effective diameter of the particles or dp, because it's not a sphere. Yeah. If it's dp, If it's spheres, dp equals to diameter of spheres. However, it is cylinder, right? So the dp, we cannot use 0.02, yeah, because it's not a spherical shapes. Yeah, and then calculate the value of A, yeah, using the equations of 3.110. Now, for part A, yeah, taking 1 cubic meter of packed bed as the basis, yeah, the total mass of the bed, yeah, is 962 kilogram. Yeah, the total mass of the bed is 962 kilogram. Yeah, nah, this mass, yeah, is also the mass of the solid cylinder. Yeah. Okay, nah, so the volume of the cylinders, yeah, since the density of the solid cylinder is 1,600, yeah, so we can find the volume of the cylinders, yeah, by dividing the mass of the packed bed divided by the density of the solid cylinder. Yeah, so we can find the volume of the cylinders only. Yeah, because this is a packed bed, right? This is the overall packed bed density. Yeah, so if we have a packed bed with the volume of 1 cubic meter, then we can find the total mass of the packed bed. Nah, yeah. Okay. Nah, and then since this 962 kilogram is also the mass of the solid cylinder, now with the density of the solid cylinder is 1,600 kilogram per cubic meter, then we can find the volume of the cylinders, yeah, by dividing the mass of the solid cylinder per the density of the solid cylinder. So it's 0.601 cubic meter. Yeah. Okay. Now to calculate the void fraction, yeah, so void fraction is the empty spaces between packings. Yeah. Nah, so to find the epsilon, yeah, it's the volume of void in bed per total volume in bed. The total volume in bed is 1. Yeah. Now, while the volume of voids in bed or the empty spaces, yeah, so it's the total volume of bed minus the volume of the cylinder, 0.6. Yeah. So it becomes 0.4 divided by 1 or 0.4. Okay, so this is for point A. Yeah, and then for point B, yeah, calculate the effective diameters of the particles. Yeah, so first we will try to find the the specific surface area of the cylinder. Yeah, so for the ends, yeah, we have 2 circles, right? For a cylinder, we have 2 circles as the end. Yeah, so it's 2 times pi times d squared per 4. Yeah, and then for the sides, it's pi times d times 8. However, since 8 is equal to d, so we can try to write it as d like this. So it becomes this. Now, the volume of the particle, yeah, so it's pi times d squared per 4. Yeah. It's a circle times the height, right, for a cylinder. Since the height is equal to d, so I can change it to d. It becomes this. Nah. So substituting, yeah, into equations 3.17, yeah, so it's SP divided by VP. So I can find that AV equals to 6 over D. Now, since diameter of particles is 6 over AV, so it's 6 per 6 over D. So it becomes D. So dP equals to D equals to 0.2. 0.02. Yeah, so the effective diameter for part B is 0.02. Now, for part C, yeah, it's easy. Yeah, we can just directly use 3.110. Yeah, so A equals to 6 over dP. I will change dP into 0.02. And then times 1 minus epsilon, I will change the epsilons, become 0.4. Yeah, so I found that the A equals to 180.3 meter to the power of -1. Okay. Any questions up until this part? If you have any questions, then you can just directly write down your question in the comment below. Okay. Now, so we go to the next slide. So still, there are several terms that we use to calculate the packed beds. So again, there is an interstitial velocity or V, and we have also superficial velocity or V accent. Yeah. So for interstitial velocity or V is the velocity of fluid between the particles. So when it passes the bed, yeah, that's the interstitial velocity, just like in this graph. Oh, let me annotate this one. Like this, yeah. Now, while superficial velocity, it's a velocity of fluid in the empty container before it passes the bed. Now, the two velocities, yeah, V and V accent, yeah, are correlated to each other by using the equations 3.111. Yeah. Okay, so you can go to John Copley's 3.111, check on the equations that is correlating the superficial and interstitial velocity. Okay. Oops. Nah. And then there is another terms again. We call it hydraulic radius or RH. RH, yeah. It's the void volume available for flow divided by the total wetted surface of solid. Yeah. You can try to see equations 3.112 up until 3.113 for all shapes or channels. Yeah, so it's actually, yeah, it's actually, you know, we knew it from chapter 2. Yeah. So that's why I asked you, does it ring a bell? Yeah, because it has similar equations that we have learned in chapter 2. Yeah. Which is to find the equivalent diameter of the channel, not particle impact bed. Yeah. Okay. So hydraulic radius or RH, yeah, is the void volume available for flow. Yeah, divided by the total wetted surface of solid. Yeah, so we can use 3.112 and 3.113, yeah, to find the RH for all shapes of channel. Yeah. Since D, yeah, the particle diameter equals to, oh sorry, it's not D of, it's not particle diameters, it's the diameter of the channel. Yeah, since the equivalent D of or the channel diameter is 4 times RH, then the Reynolds number for packed bed can be calculated using the equations 3.114 and 3.115. Yeah, however, it is agreed after this that for finding the Reynolds number in packed bed, we will use 3.115 by air gun. Yeah, so I will go to John Copley's. Yeah, so yeah, 3.111 here, yeah, is the correlation equation for interstitial and superficial velocities. Yeah, and then for us to find the hydraulic radius or RH, yeah, we will use this, yeah, cross-sectional area available for flow divided by wetted perimeter. Yeah, or we can also say that it's epsilon, yeah, volume of voids, yeah, divided by A, yeah, okay, yeah, wait. Okay, so this is our H, yeah, we can define it as epsilon, volume of voids, per volume of bed, yeah, so the void fraction divided by the wetted surface per volume of bed, or A. Okay, nah, and then so if we want to find the diameter D for a channel, so it's the diameter of the channel. If we want to find the diameter of the channel, then we can use this equation. D equal to 4 times RH. D equals to 4 times RH. Okay. Yeah. Nah, then if we want to find the Reynolds number for packed bed, there are two equations here, 3.114 and 3.115. Yeah, however, we will use these equations, yeah, not these equations, yeah, for the for finding the Reynolds number in packed bed. Yeah, so we use this, yeah, not this. Okay, we use this. Okay. Nah. Okay, so the next term is the pressure drop in laminar flow. So pressure drop that is caused by the form drag and frictional drag, yeah, between the fluid flow and the immersed object. Yeah, this pressure drop can be derived by using the Hagen-Poiseuille equation. Yeah, and it becomes, yeah, by using several arrangement, then it becomes the Black and Kozeny equations. Yeah, which is shown in John Copley's equations 3.116. Oh my God. 3.116 here, or 3.117 here. Yeah. So you can use this. Yeah. Or you can use this. Yeah. Nah, but this, yeah, but the equations in 3.117, yeah, is only valid for laminar flow, and then with void fraction less than 0.5. Yeah, so the void fraction is less than 0.5. And then the flow is in laminar flow. Yeah, and then NREP is less, oh yeah, betul. Sorry. Less than laminar flow. Yeah, so it's less than 10. Yeah, less than 10. Okay, so this equation is valid if we have an NRE in packed bed less than 10 or in laminar flow, and the void fraction here less than 0.5. Yeah, this one also, yeah, alpha, this one also valid only if the flow is in laminar flow. Yeah, this is valid only if it's laminar flow. This is only valid for laminar flow. Yeah, but it's also has an additional requisites, yeah, which is the epsilon is less than 0.5. Well, for this, it doesn't have any validity. It doesn't have any restriction for the epsilon value. Yeah, it's only they said that it's only for laminar, yeah, but there is no restriction for epsilon value. However, this is for laminar, and there is also a restriction for the epsilon value, which is must be less than 0.5. Okay. Any question? Yeah. So you can choose either 3.116 or 3.117. Yeah, but once again, it depends on the epsilon value. If it's less than 0.5, you can use this one. Yeah. If you don't want any restriction on the epsilon value, you can use this one. But both, yeah, are only for laminar flow. Okay. Any question? If you have any questions, then you can try to write down in the comments below, okay? Nah, and then we go to the Darcy's law. Yeah. So the Darcy's law is usually used for packed bed with a very small void or very fine packing. Yeah, so the size of the packing is very fine. So it has a very small diameter. The packing has a very small diameter. Yeah. Now this Darcy law, yeah, is used to determine the permeability of the packing to the fluid. Yeah. So if it's very fine, so of course it will be difficult for the fluid to pass over the immersed bodies, right? Now, so this Darcy law is used to determine the permeability, yeah, of the packing to the fluid. Okay. Nah, to calculate the pressure drop, yeah, which is can be to calculate the pressure drop, yeah. Since this is laminar flow, we can use 3.117, right? But for Darcy law, we can derive it into 3.128, yeah. With K is the permeability coefficients of the packing, yeah. And then QXN is the superficial volumetric flow rate. And then A is the cross-sectional area of the bed. Okay, so if the packing is very fine, yeah, if the packing has a very small diameter, yeah, we cannot use this equation 3.117, yeah, but we can use the derived equation, yeah, in the 3.128. Let me go down. This one, yeah. So he can use these equations, yes. So this is actually the derivation equation from 3.117. Yeah. Yeah. So this is the Darcy law. Yeah, the Darcy law for laminar flow to determine the permeability of the solid to the fluid. Yeah. Okay. So Qxn over A equals to minus K per mu times delta P divided by delta L. Okay, so Qxn is the flow rate. And then A is the cross-sectional area of the packed bed. And then K is the permeability coefficient. Mu is the viscosity of the fluid. And then delta L is the length of the bed. And then this is the this is the pressure drop. Yeah. Okay. So instead of using 3.117 for laminar flow, yeah, for fluid flow past immersed object, with a very small diameter, yeah, we will use the Dorsey's empirical law. Yeah, we will use this to find the pressure drop or the permeability coefficient and else. Oke, okay. Ya, jadi kalau 3117 tadi digunakan untuk laminar flow, ya, dengan epsilon kurang dari 0.5, ya. Nah, untuk kita mengetahui pressure drop pada pressure drop pada pack bed yang memiliki diameter packing sangat kecil. Nah, kita tidak lagi pakai equation 3117. Nah, kita pakai equation 3128. Ya. Oke, kita bisa pakai pendekatan ini ya instead of 3.117. Oke. Nah, and then we go to the next subtopic, which is the flow in packed bed in the turbulent. Yeah, so actually similar to the laminar flow, the pressure drop in the turbulent flow can be derived from 2.105 into equations 3.118. Yeah. So I will try to open the Jankov, please. Yeah. So actually the pressure drop for turbulent flow in packed beds, yeah, we can use this equation. Yeah. Nah, and since 3F, yeah, since 3F equals to 1.75, so 3 times fanning friction factor, yeah, 3F actually based on the experimental data, yeah, 3F equals to 1.75. So we can change this 3F becomes 1.75. So it becomes 3.119. Yeah. And this is only for turbulent flow. Okay. So these two are only for turbulent flow. Yeah. Okay. So this is the general equations. Yeah. And since based from the experimental data, 3F equals to 1.75, then we can change 3.118 to 3.119 like this. Yeah. We call this as the Berg-Plummer equations. Yeah, and it's only valid for turbulent flow or higher than 1000. The NRE higher than 1000. Nah, Ergun, sorry, let me go back to the PowerPoint. Nah, okay, so as a note here, yeah, hereafter, we will use equation 3.119, yeah, for pressure drop calculations in Reynolds number in packed bed higher than 1000. Okay, so we will use 3.119, yeah, for pressure drop, for calculating the pressure drop in the Reynolds number in packed bed higher than 1000. Okay. Nah, Ergun, yeah, Ergun proposed a general equations of pressure drop in packed bed for all type of flow, laminar, transitional, and turbulent, yeah, which is shown in equations 3.120 and 3.121. Yeah. Okay, so we go here. Yeah, this. Yeah. So we can use this or this. Yeah. So actually the general equation is 3.120 here. However, after some rearrangement, it can becomes a dimensionless equations. So it becomes like this. Yeah. Nah. Okay. So I will go back to the PowerPoint. Now, if the NRE, yeah, so if the Reynolds number is less than 10, yeah, so the equation of 3.120 and 3.121 can be simplified into 3.116 or 3.117. Yeah. Remember, if it's 3.116, it's only for laminar flow, but there is no restriction in the epsilon. While for 3.117, there is a restriction as well for the epsilon, which is less than 0.5. Now, however, if the NRE impact bed is higher than 1000, so it's turbulent, so these two equations can be simplified into 3.119. Okay. Yeah. So it depends. If you have a value of NRE less than 10, then you can use 3.116 or 17. While if your NRE is turbulent, you can simplify it into 3.119. Nah, the equations, yeah, so these equations, 3.120 and 21, can be used for gases as well, where the density of the gas, yeah, is defined as the arithmetic average of the inlet and outlet pressure. Yeah, and can be calculated using 3.122. Okay, so I will go into John Coplis. Yeah. Hey, oh my. Wait, let me. Yeah. Nah, this. Yeah. So for gases, usually, yeah, the pressure will change, right? Yeah. So these equations, yeah. Nah. So these two equations can be used as well for the gases. Yeah, however, since the pressure changes throughout the process, yeah, for gas, yeah, so of course, we have to know the P average, yeah, in order to calculate the flow average or the density average, yeah. Now, so the P average, yeah, the P average is actually equals to the arithmetic average of the inlet and outlet pressure of the gas. Yeah, and by using this average pressure, then you can find the density average. Yeah, by using this equation. And then you can use 3.120 or 3.121 to find the pressure drop. Okay. Yeah. Okay. Nah. So let me read, or wait, let me check whether there is another. Nah, for compressible fluid, yeah, the superficial velocity or Vxn changes throughout the beds. Yeah, but not the superficial mass flux. Yeah. Now, when can we classify the fluid as compressible fluid? Yeah, when the pressure drop in packed bed is higher than 10%. Yeah, based on the initial pressure. So it's similar to what we have learned in chapter 2. Yeah, so compressible fluid, yeah, is when a fluid has a change in pressure by more than 10%. However, if it's less than 10%, we can say that it is incompressible fluid. Yeah. Nah, for the compressible fluid, yeah, the superficial velocity, yeah, changes throughout the bed because it will, have an impact with the solid, the immersed solid. Yeah, but for the mass flux, it will not change. Yeah. So we go to example 3.14. Okay. So we have air flowing through a packed bed of spheres having diameter of 12.7 millimeter. And then the void fraction of the bed is 0.38. And the bed having diameter of 0.61 and height of 2.44. Now the air enters at the bed at 1.10 atmosphere at the rate of 0.358. Yeah, and calculate the pressure drop of the air in the packed bed. Yeah, the average molecular weight of air is 28.97. Nah, okay, so it's air. So from appendix A3, we can find that the mu is this, yeah, at this particular temperature. And then since we know, yeah, since we know that the bed has a diameter of 0.61 meter, yeah, so we can calculate the cross-sectional area of the bed. Yeah, so it's A equals to pi over 4 times d squared. Yeah, so put 0.61 here. Yeah, so we found it here, this 0.2922. Yeah, now, and since the mass of the air that is entered the bed is at the rate of 0.358 kilogram per second, then we can find the mass flux, yeah, by dividing the mass with the cross-sectional area of the bed. Yeah, so it's 0.358 divided by 0.2922. So it becomes this. Yeah, so this is the superficial mass flux, not the superficial velocity. Yeah, because the superficial velocity will change throughout the bed, while the superficial mass flux will not. So we will use superficial mass flux. So this is dP, delta L, and then inlet pressure here, yeah, 1.1 atm. Yeah. Nah, so by using the packed bed Reynolds number equations, yeah, the diameter of particle times superficial mass flux divided by mu times 1 minus epsilon, then we will put all the value that we know here. Yeah. And then we found that the NRE is 1,321, so it's a turbulent flow. Yeah. And since this is for gases, yeah, and the density we want to use is the average density, yeah, in the inlet and also outlet. And since the inlet and outlet pressure will have a different pressure as well as different density, so we will have to use a trial and error solution. Yeah, because this is a gas, yeah, and the density that we will use is the average density, yeah, which is at the inlet pressure and outlet pressure. Yeah. Okay. Yeah. There is a pressure drop, right? Yeah. So the pressure at the inlet and also outlet will be different because there is a pressure drop. And since this is a gas, yeah, pressure will significantly affect the density. So that's why, yeah, we have to use the average density, yeah, in this equation. Now, and since we do not know the outlet pressure, we only know the inlet pressure, then we will use a trial and error solution. Yeah, we will assume first the outlet pressure. Yeah, and then, and then they assume that the delta P, yeah, they assume that the delta P between P1 and P2, yeah, is 0.05 times 10 to the power of 5. So we know that the P2 equals to 1.065 times 10 to the power of 5 Pascal. Nah, by using these two values, P1 and P2, we can find the P average. Yeah, so this is P1 and this is P2 divided by 2 becomes this. So we will use this P average in this equation. Yeah, and then M is the molecular weight of the air. R is the Raoult's, the ideal gas constant, the Raoult's gas constant. And then T is the temperature of the air. Yeah. So we found that the rho average is 1.221 kilogram per cubic meter. Yeah, and then after this, we put all the known values, yeah, into equation 3.121. Yeah. Then after that, after some rearrangement, then we can find that the delta P is 0.0497 times 10 to the power of 5 Pascal. Now, since this is close enough to the delta P assumed here, yeah, so we can say that a second trial is not needed. Okay. Okay, any questions up until this part? If you have any questions, then you can go to the comment section and write your questions down below. Okay. 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 So the next subtopic is about the shape factors. Yeah. So as I previously mentioned, that the packing has various in shapes and are often irregular. Yeah. If it's disc or if it's sphere, yeah, or if it's a cylinder, it's easy for us to find the surface area, the volume. Yeah, however, if it's irregular in shapes like this, yeah, ceramic pearl settle, yeah, how do you calculate the specific surface area? How do you calculate the volume, right? It's difficult, yeah? Or like this, the metal pole ring, yeah? How do you calculate the surface area or the volume? Yeah, it's difficult, yeah? So in this subchapter, we will discuss how to calculate, yeah, the equivalent or effective diameter of the particle so that we can find the dP, yeah, which is used often in the calculation of NREP, yeah, or Reynolds number impact bed, yeah. Let me open all. Nah, okay. So the effective or equivalent diameter of an irregular particle dP, yeah, is the diameter of a sphere having the same volume as this irregular particle. So this equivalent or effective diameter or irregular particle is actually the diameter of a sphere having the same volume as the irregular particle. So let's say if I have a ceramic pearl settle like this, yeah, so the dP of this is actually the same as the diameter of a sphere having a same volume as this irregular particle. Yeah. So we can use, sorry. Yeah. we can use the sphericity shape factor, yeah, or tau s, like this, which is expressed as pi times square of the diameter particle divided by specific surface of the particle. Yeah. Okay, so we can use this tau s, yeah, which is expressed as these equations to find the dp. Yeah. Okay. Yeah. So to find the equivalent or effective diameter of a irregular particle, yeah, we will use this sphericity shape factor or tau s, yeah, which can be expressed as this. Okay. Now, so we can find the dp by using the equations 3.123 and 3.124. Yeah. To find the AV, yeah, and 3.125 to find the A. Yeah. So the sphericity shape factor for sphere is actually equal to 1 for cylinder, whose diameter equals to its own length is 0.874, and for cube, it's 0.807. Now for cross material is 0.6 to 0.7. For other shape, you can see in table 3.11. Yeah, so I will go to Jen-Go, please. Yeah, so here, yeah. Okay. So it's similar, right? Yeah. So AV or SP over VP equals to 6 over dP for spherical. Yeah. Okay. However, since this equation is for the irregular shape, then this tau s must not in the value of 1 only. Yeah. For sphere, it's AV equals to SP per VP equals to 6 over dP. Yeah, as the one in this part. Let me go up this one. Yeah, AV equals to SP per VP, and for spherical particle, AV equals to 6 over dP. Right? So it's actually similar to what we see here as well. Yeah. Yeah. AV equals to SP per VP. Yeah, SP per VP. Yeah, and this AV also equals to 6 over tau s times dP. And so it's actually similar, right? But in this equations, in this 3.123 and 3.124, we have tau s. Yeah, additional term here as tau s. Yeah. Now, if it's for spherical, since spherical has a tau s of 1, yeah, so it becomes 6 over dP only. Yeah, nah, but for the other irregular shape, yeah, the tau s will not have a value of 1. Yeah, but it has a value of other. Yeah, like cylindrical. Yeah, it's 0.874. Yeah, for cube, it's 0.806. Yeah, while for another shape, yeah, you can see here. Yeah, let's say for both settles, the shape factor or tau s equals to 0.3. Yeah, so you fill it as 0.3. Yeah, for coal dust, it's 0.73. Yeah, so later it will be 0.73 here. Yeah. Okay, but for spherical, yeah, you can see for spheres it's 1. Yeah, So it's 1. Yeah, so it becomes 6 over dp, just the same like in the equations in the previous subchapter. Okay. Okay. Okay, so oops. Nah. In the previous subchapter, I told you that the packing, yeah, is assumed to be uniform. Yeah, as I said previously in this slide, I think. Wait a minute, let me check. Nah, this, yeah. So in this subchapter, yeah, in this subchapter, flow in packed beds, yeah, it is assumed that the packing is uniform. Yeah. Nah, however, yeah, okay. Nah, however, yeah, in this subchapter, yeah, we will talk a little bit. How about if we have a mixture of particles? Yeah, so packed bed can use one type of packing. However, some packed bed also use several types of packing. Yeah, with a certain composition. Yeah. Okay. So previously I told you that in that subchapter, we assume that the particle of the packing is uniform. Yeah. However, in this subchapter, we talk about the mixture of packing particles. Yeah. Because some packed bed will also consist of several types of packing material. Yeah, with a certain composition. Nah, to calculate the effective or equivalent mean diameter, yeah, you may use first the equations of 3.126 to find the average specific surface area or AVM. Yeah, and then you can use the equations 3.127 to find the effective or equivalent mean diameter dpm. Yeah. Okay, so I will go to Chanko, please. Oopsies. Yeah. Nah, okay. So for the mixture of particles, yeah, we can try to find the AVM or the mean, yeah, of AV, yeah, or the mean specific surface, yeah, by using these equations, yeah. So sigma times the mass fraction of the particles times its own AV, yeah. And then after we find this AVM, we can find dpm by using this equation, 3.127. Yeah. So let's say, yeah, let's see in the example 3.15, yeah, for us to understand a little bit better about these two equations. Yeah. So we have a mixture of packing materials, yeah, contains three sizes of particle. 25% by volume of 25 millimeter in size, 40% of 50 millimeters in size, and 35% of 75 millimeter in size. The sphericity of these three particles are 0.68. Calculate the effective mean diameter. Nah. Oh, sorry. So then it's not the mass volume, but it's not the mass fraction, but the volume fraction, teman-teman. Yeah. So Xi is the volume fraction. Yeah. AVI, it's their own AV value. Yeah, it's their own mean specific surface. It's their own specific surface. Yeah. Okay. Nah. So based from the example 3.15, we know that X1 is 0.25 with the particle diameter of 25 millimeter. X2 is 0.4 with the particle diameter of 50. Okay, correct. And then X3 is 0.35 times with the particle diameter of 75. And then we know that the sphericity of these particles, yeah, the sphericity factor of these particles are 0.68. Yeah. So if we want to find the effective mean diameter, then we can try to use this 3.126 equation. Yeah. Okay. So 1 divided by 0.25 divided by sphericity times dp. And then 0.4 divided by 0.68 times dp2. Yeah, and then x3 divided by 0.68 times dp3. Yeah, so we found that the effective mean particle diameters is 30 millimeters. Yeah. Okay. So that's all for today's class. Yeah. If you do not have any questions, yeah, please work on the 4 problem. Yeah. Okay. That you can see in the PowerPoint. Yeah, because in the PowerPoint I give you 4 number of assignment that you have to work on. Yeah, so please do the 4 number assignment, and then you can submit it the latest at Friday at 9 a.m. sharp. Okay. If you do not have any more question, then I will end the class here. Thank you very much.